So, hello everyone. In this video, I will present my work for assignment 3. This assignment has two parts. In part A, I worked with image convolution. I import an image, converted it into arrays, and can build direct 2D kernels to detect lines and edges. In part B, I trained the convolution neural network on the CR10 dataset, analyzed the result, checked for fitting, then improved the model by adding extra convolution layers and dropout. So, what I did first, I was import the required libraries. NumPy is used for array operation. PIL helps open the image. Matplotlib is used to display image. Request downloads the image from URL. By test AOL lets me store the download image in memory. Then I used request get to load the image of the car from the URL. After that, I converted the image into an NumPy array. And this gave me 3D presenting the image in RGB format. So next I display the original image and check the shape of the array. The shape was the image shape is 140, 359 and 3, which means 140 pixels in height, 359 pixels in width, and 3 color channels, red, green, and blue. I also compare the color channels to show that they are not equal. This confirms that each RGB channel stores different information. So then I selected only one color channel, is channel 0, which is one of the RGB channels. So the image became a 2D array instead of 3D one. This is useful because convolution is easier to demonstrate on a single channel image. At this point, the image is no longer treated as a full RGB image. This becomes a 2D intensely matrix that can be processed with kernels. So then, before applying different kernels, I created a simple example of 2D convolution. I first padded the image with zeros around the border. Padding is necessary so that on the kernel can still be applied to edge pixels. Then I created a kernel. The first kernel is basically a JD style kernel because the center has value 1 and everything else is 0. So when its kernel is applied, the output looks almost the same as the original image. So to avoid the same image as you see. To avoid repeating the same code, I created a reusable function. The first function squash pixel value keeps pixels values between 0 and 2055. This is important because of converge can produce values below 0 or above. The second function conv to the kernel applies any three kernels to the image. This function in the main function I used for the rest of part A. So let's start with part A question 1. Line detection. Oh, my bad. So this kernel is designed to detect horizontal lines. The middle row has positive values and the rows above the below have negative values. So is there a strong horizontal pattern in the image? This kernel gives a strong response. When uploaded the results, the horizontal edges and lines like regions of the car became much more visible. So for question 1, I created a kernel to detect 45-degree diagonal lines. This kernel varies one diagonal direction more strongly than the other neighboring pixels. When applied into the car image, diagonal features such as windshield edges, roof lines, and angel body lines became cleaner. After applying it, the output applies the diagonal lines that run in the other direction, such as opposite slants in the car body and window structure. So, edge kernel. This kernel detects detects directional channels in pixel intensity. It highlights edges by comparing opposite corners and nearby regions. The result shows visible outlines of the car, especially where the image intensely changes sharply. Um, so this kernel is similar to a Laplacian operator. It takes edges in multiple directions at once by measuring how different the center pixel is from its direct neighbors. So this is stronger edge detection kernel. It compares the central pixel to all 8 surrounding pixels, and because of that, it produces an even stronger outline of the object and detects edges in all directions. Among the edges, kernels is one usually produce one of the clearest boundary enhanced outputs. Now we'll move to part B, where I trained a convolution neural network on the CFR10 dataset. So I start with importing libraries and loading the dataset. Uh, then building the neural CNN model. My first model was simple with CNN with 5 layers. I will explain layers. So conv2D with 35 or 32 filters. This layer learns local features like edges, texture, and simple shapes. Max pooling 2D. This reduces the spatial size of the features, maps, and keeps the strongest features. Flatten. This converts with 2D features maps into 1D vector. Dense with 128 units. This combines the learned features into a more abstract representation. Dense with 10 units and softmax. This outputs probably for the 10 cipher and 10 classes. So compiling the model, Adam is commonly used um, because it trains efficiently. Custom callback and training. I created a custom callback to print training and validation accuracy over 5 epochs. Then trained the model for 10 epochs using the training set and validation it on the test set. So question 3 is overfitting. Yes, the network shows signs of overfitting. The training actually kept increasingly steadily, but the validation accuracy improved only up to a point and then started to level off. That means the model was becoming better and rising the training set, but not improving as much on unseen data. So how many layers and what types is question 4. The original sequence model has 5 layers, as I showed. Convert 2D, max pooling 2D, flatten, dense with 128 units, and dense with 10 units using softmax. So question 5 is purpose of each layer. So conv2D learns local visual patterns such as edges and texture. Max pooling 2D reaches the size of the feature maps and keeps the strongest response. Flatten covers the feature maps into a single vector. Dense 128 combines extract features into a higher level, and dense 10 softmax outputs the probability for each C4 10 classes. So mm, next deeper model. For question 6, I added one more convolution block, another crown 2D and another max pooling 2D. This makes the model deeper and gives it more capacity to learn richer features. So comparing the original and deeper model. So at the same time, the deeper model also increased the difference between training and validation accuracy. So although it learned more, it also showed stronger signs of overfitting. So for the question 8, adding dropout, I added dropout layer after flatten. This dropout rate was 0.5, which means that during training, half of neurons in that layer are currently turned off at each step. So question 9 is purpose of dropout. So dropout is a regulation technique used to reduce overfitting. During training, dropout randomly disables some neurons, so the network cannot depend so much on the single path. At the same time, dropout is turned off and the full network is used. That means dropout helps the model generalize better. So overall, this assignment helped demonstrate both classical image processing with convolution and modern deep learning using convolution neural network. So thank you for your attention.